Okay, so f of 3 means 3 places to the right of the decimal, so, because this n represents that 3, so this is 2. This one would be 8, because f of 4 would be 8. This one, f of 5 is 5. F of 6 is 7. F of 7 is 1, 4, 2. Uh-oh. What is f of 10?
That'd be 8.
How do you know that?
Because
There's no f of 10 here.
it's just going to keep going. It never actually solves, it just...
Okay, okay. I see what you mean. Okay, so it repeats. So I go 1, 4, 2, 8, 5, 7. 1, 4, 2, 8, 5, 7. Okay. Okay, so if that's the pattern, what will f of 18 be? 7. Okay, Leo, how'd you get that?
Well, 7 is in 6.
7 is at 6.
6 times 3 is 18.
6 times 3 is 18. So that works because it'll be 7 at 6, it'll be 7 again at 12, and it'll be 7 again at 18. Okay, so if f of 18 is 7, what is f of 19?
1.
1. What would f of 30 be?
7.
7. So f of 32
4.
is 4. Is everybody good so far? What about f of 600? 7, because we could go to 6 100 times and it'd be 7. And then, so that would make 599 5, because it is 1 spot less than 600, so it would be right here. Is everybody good? Making sense? Okay, so explain that logic again. What were we doing? Why is this working? How can I tell what f of 600 is without counting on my fingers?
So repeating 6 decimals.
There are 6 decimal places, and then the pattern repeats itself, right? So the pattern repeats every 6 decimal places. Okay, so now what they want us to do is to graph this function. So remember, this notation we've used now for 3 years. F of x equals y, right? So the 3 is the x value, the 2 is the y value, so that's an ordered pair, 3, 2. And then 4, 8 is an ordered pair, and 5, 5 is an ordered pair. So go ahead with that in mind and graph, use this down here, and graph those ordered pairs up there. And go ahead and connect the dots. It makes it easier to see. Okay, so if I graph them, it looks kind of like that. Now it doesn't go all the way back to the y-axis, but I can make it go back to the y-axis. So I think I'll do that just because I can.
Teachers, pardon this interruption. I have a quick announcement from Mrs. Coach Vaughn. Sophomore girls need to meet at the cages at 4 o'clock, and practice will be no longer than an hour. Thank you.
Okay, so now if you look at this graph, so I went ahead and I backed it up because I figured out the pattern, right? So number 5 says, for what value of n does f of n attain its maximum value? So where is the peak? Where are the peaks? Because there's more than one, right?
3 and 10.
It happens at 3, and then it happens again at, actually it happens at 4. Yeah, 4. It's these, I hate these, the way they number these, because it's to the right, they're in a bad place. But it's at 4, and then again at 10. If I had more graph, where would the next one be?
16.
16. So now they didn't ask this, but where are the valleys? Where are the lowest peaks? 1, 7, 13. If there was another one, where would it be?
19.
And if I were, let's say we find this particular point, this critical value. It's at 2, and then again at 8, and where would the next one be? 14. All these critical values keep repeating themselves how often?
6.
Every 6. So this function is what we call a periodic function. What do you think that means?
For a period of time, it's the same.
Exactly. It does something for a period of time. And when that period of time is over, it does that same thing again. So this is what we call a periodic function. We deal with periodic functions all the time. Every day, we deal with a 12-unit periodic function. What would that be?
Time.
Time. Because every 12 hours, it repeats itself. 1 o'clock comes around again 12 hours from now. We deal with days. Every 7 days, Monday happens again. So that's periodic. So we deal with lots of periodic things. So we are very familiar.
Every 4 years is
Trig is periodic. So that's why we are going over periodic values. So on this worksheet, it's super, super, super easy. But let me explain to you again.
distribution. You do it.
You can do it. That would be great if you want to do it. I'm all for it. Do it, do it, do it. Because I gotta go pick up my kids and I'm running around and chewing my head off. So do it.
Depends on
Okay, I
your
didn't think
religion.
this would go well, but
Okay. So now they've just reminded me. At the top, they give me a picture of the unit circle. And they've reminded me of what I already know. Sine is y, cosine is x, tangent is y over x. They reminded me of my reciprocal values. So then we're just going to graph what our trips around the unit circle look like. So this particular table is just meant to help you graph it. So sine is your y value. This is like ridiculous easy. Sine is your y value, so it's 0, -1, 0, 1. Alright, so now that I have those, disregard this middle point. They were just helping us get our way around the unit circle. What we are actually graphing now is theta and sine theta. If you look at your graph down here, it is no longer the x-axis, it is the theta axis. And your y-axis is now the sine theta axis. So this first thing is my first ordered pair, -π0. So I'm going to go to -π0 and put a dot. And go ahead real quick and just plot all those points.
Do you want me or us to connect it?
Actually no, and I will explain to you why in just a second.
Feel the burn. Oh, wow.
Now, the reason that I did not have you connect the dots is because if we connected the dots, we would be tempted to just make them kind of like the one we just did. They would look like peaks and valleys and be like it would look like this. You would probably have connected them like this. Because in our world that makes perfect sense and that's how we connect things. But what this really looks like, and I'm going to put it up because I am a horrible grapher. Y'all know that. So what it really looks like is this. It's a wave. That's the sine wave. So it's curved. Now, if you think about it, this makes perfect sense. We are graphing what sine is. Sine is the y value, right? So as we go around the unit circle, the y value is positive until you get to pi, and then it is negative as you go around. And then at 2 pi, it goes positive again. So if you look at our wave, it's positive until we get to pi, and then it's negative. Does that make sense?
Yeah.
And it makes sense that it's curved because it's a circle. We're going around and around and around. So it makes sense that it's a wave, yeah? Okay, so now do the same thing, but this time we've switched to cosine. So now when we fill in our ordered pairs, this time we're looking at the x values. So fill them in and plot them. And now you know it's supposed to be curved. So go ahead and connect the dots. Curvy if you can.
Cookies is bad.
I'm a horrible grapher, so I totally understand. Mine never look like they're
They
supposed
look
to.
like squares.
Why does it look like a heart rate monitor? That's what mine always look like. Of somebody with a condition. With a bad condition.
Like it's annoying me because I can't get it right. No.
Okay, so cosine.
I think yours.
Now this, you can see them both up there at the same time. Cosine looks like this, which also makes perfect sense. We're graphing the x values here. So if you think about the x values, they are only positive until we get to pi over 2. And then they go negative. And then they stay negative, and they don't go positive again until 3 pi over 2, and they go positive. So if you look at it, it makes sense. They're positive until pi over 2, then they stay negative until 3 pi over 2. And then they go positive again. So it goes around and around the unit circle. That's why it's curved. So on the back, if you'll flip over to the back, we're going to put them in our calculator. Now, on your calculator, there are a couple things you need to know. Number one, it needs to be in radians. The graphs do not look nice if they're not in radians. So put your calculator in radians if you're not already there. And the other thing is, after you plug it in, when you hit zoom, I don't know where my inspire is. When you hit zoom, there's a button that says zoom trig. If you will hit zoom trig, it will put your values. Actually, I really need to know where my inspire is. Let me borrow one of y'all's real quick. Since I'm videoing it. Let me, Travis needs that real quick. Let me borrow Austin's. Travis needs to hold this. Okay, so I'm gonna put in sine x.
Yeah, they piled that, by the way. That wasn't me.
Oh, nice. I didn't even notice it. Okay, so I hit sine x, and then if you hit, and there's my sine wave, but I'm going to hit menu, and on my zoom window, if you see number 8 is zoom trig. If you'll notice, now it's counting by decimals, but notice what this last decimal is. 6.28. What is that?
2 pi.
2 pi. So this is 1 trip around the unit circle. So it kind of helps. Now, another thing that might help, this particular worksheet was done based on the 84. And on the 84, it doesn't give all these little hash marks in between. So if you want yours to look like theirs, I could hit menu and window zoom. And on my window settings, I could, instead of it to scale auto, the way that that is scaled, there's a hash mark at every half pi. So I can plug in pi divided by 2, and it should give me hash marks at every half pi, just like the worksheet does. Yeah. It gives you the decimal version, but each of these hash marks represents a half pi. Does everybody follow me? Okay, now, on the x-axis, it is counting in radians. Pi, half pies, 3/4 pies, all that stuff. But on the y-axis, it's just counting 1, 2, 3, 4, 5, just like normal. So we're just going to answer these questions. on that. So, what is the y-intercept of sine? Looking at the graph that you got there.
0?
0. Where do the x-intercepts occur?
At pies.
At the pi's. So at pi, and then again, another one occurs at 2 pi and 3 pi. So you could just put at the pi's. It really wouldn't be an apostrophe. Sorry. Fix my English. It's just pi's with an S. It's not possessive of anything. That pi does not know anything. Okay, what appears to be the domain of y equals sine x?
Negative.
Negative infinity to infinity, or all real numbers, because we could go around and around this unit circle as many times as we please, either in the positive direction or the negative. What about the range, though?
Oh,
Negative 1 to 1,
Yes, unit circle.
and it is included, because it actually touches those places. This would be negative 1 to 1.
But is that the reason? Because it's still...
Yeah, because our radius is 1, and so as high up as it can go is 1, that's it. Okay, so what value of x does the function reach a maximum? At the pi over 2's. Now, it isn't just the pi over 2's, because that almost would imply that it happens at 3 pi over 2 and doesn't. It happens at pi over 2, for sure. And then what? Where's the next place that it occurs? 5 pi over 2. It happens at negative also, if you go backwards. It does, it does. Because we start with pi over 2, I'm just going to go in the positive direction, but it does go into the negative direction also. It happens at 5 pi over 2. It is going to happen again at 9 pi over 2. And again at 13 pi over 2. What would the next one be? 17 pi over 2. What am I adding each time? 4. 4 pi over 2, which is what? 2 pi. Where would that come from? A full trip around the unit circle. So this is periodic. Its behavior repeats every time it goes around the unit circle again. Okay, so at what values does the function reach a minimum? So where's the first minimum? And you can give the negative one if you see it. If the negative one's the first one you see. What's negative? Right, it's at positive 3 pi over 2. Or if you start at the negative one, negative pi over 2. Now we know this thing is going to repeat every time it goes around the unit circle. So the next one would be at 3 pi over 2. And then 7 pi over 2. And 11 pi over 2. Because it repeats every 4 pi over 2. And that can just dot, dot, dot. All right, here's a good question to jog your memory. Is sine even, odd, or neither?
Odd.
How do you know?
So you rotate it and that.
Very good. It is odd because it has rotational symmetry. If you turn it upside down, it looks exactly like it does right side up. So, now we're going to do the same thing for cosine. So you can just change your wave to a cosine wave. All right, what is the y-intercept of cosine?
What?
1. This time, where do the x-intercept, where do those happen? The
X-intercepts?
Yep.
At
At pi over 2, or the half pi's. All right, domain of cosine.
Negative.
Negative infinity to positive infinity, or all real numbers. What about the range? Negative 1 to 1. At what values of x does this function reach a maximum? So what about cosine? Where are the maximums on cosine?
Like the 2 pies.
At the 2 pi's, or the even pi's, right? Because it goes 2 pi, 4 pi, 6 pi. The first one actually happens at 0, and then 2 pi, 4 pi. Or you could go back. Negative 2 pi. 4 pi. the minimums? Where are they? 3 pi over 2. And then it's going to happen again. Isn't it 3 pi over 2? It's at pi. It's at pi. It's at pi. And then the next one happens at 3 pi, and then 5 pi. So the odd pies. The even pies are the maxes, the odd pies are the mins. Okay, what is cosine? Odd, even, or neither? It is even. Why?
Fold it.
This one can fold, right? This is y-axis symmetry.
They're meant to be.
All right, these two graphs have an awful lot in common. It asks you to compare them graphically. Just off the top of your head, what are the things they definitely share in common? Domain and range are the same. They look almost the same, don't they? I mean, they're the same behavior, there's this wave thing. It's just shifted over, good. So this is the easy way to remember. When somebody puts a graph up for you to remember which one's which. This is a snow cone. Sine starts down and goes up like the snow. Cone starts up and goes down. Sine and cosine. That'll help you remember which one's which. It's a snow cone. We'll try that tomorrow.
Did you just say death in despair?